Welcome back. In the last session, I didn't give you time to write down. Maybe you can write down, then I'll see the third one, which is nothing but saturation part. Okay, I don't have space to write over there. Therefore, let me write the third one later. You take it. Therefore, cutoff and saturation both are covered with respect to the voltages. Okay, take it. But I don't know, in the previous session, if you already noted down, that is fine. But if you don't write, just I'm giving you 2 minutes to write down. I hope this is done. This is for the saturation part. Okay. Now write down for the active region part. Let me erase this. The third one. Now, obviously, when VBE is greater than or equal to 0.7, and let us say the other one, VCE is greater than 0.2, and VCE is greater than 0.2, which is intermediate stage, right? Now, we know that when VBE is greater than or equal to 0.7, obviously, right, let us say your emitter junction, that is in forward bias, that is true. Okay, maybe let me take the same and I say capital 3, this is Roman 3. Now this is greater than or equal to 0.7, let us say 0.75. I'm just giving you a some example. 0.75. Then VBE, we have more IB, more IC, then more drop across RC, but not completely 10 volts, because that case we already seen, because you are not giving maximum VBE. It is intermediate VBE, then intermediate base current, intermediate collector current, intermediate voltage, let us say 5 volt. Then what you get at the output? At the output, let us say, because let us say this is 5 volt, then the remaining voltage KVL. What is output KVL? This voltage is equal to this voltage plus this voltage. Right? Earlier, entire voltage we had seen here, therefore only 0.2 or 0 we had seen here. But now it is only 5 volt, which is intermediate, and this is 5 volt. Therefore, let us say it is around 5 volt. Let us say, like half of the midpoint of rail to rail. Typically, that is what people try to concentrate to keep the transistor in active region. Therefore, whenever you get swing about it, therefore it will be 10 to 0 if output DC voltage exactly is at 5 volt. The DC voltage is biased in the transistor to keep in active region. Now, when I say this is what is 5 volt, then Then tell me, this is 5, this is 0.75. 0.75 0. Definitely this is in forward bias. Now this is 0.75, right? But this is 5. 5 and then 0.75. If you see here, right? This is 5, sorry, 0.75 and then 5. Definitely N is connected to 5, P is connected to 0.75. Still that is, means that is definitely reverse bias. Therefore tell me, if J is in forward bias and JC is in reverse bias, then surely the transistor is said to be in active region. This is what is called active region. The transistor is in active region, then how is it configured? Means what is the equivalent circuit, right? Now you see here, this is collector, emitter, base, right? Let me give you first of all ideal model, then practical model. Ideal model means people call this as current controlled current source. It is not on resistor, it is not off resistor. Means it is not open circuit, it is not short circuit, it is a current source. But the output current, the current which is what is flowing through collector to emitter, right? That current is controlled by your base current. That is what is controlled by your base current. Therefore, if you ask me the equation, which is nothing but IC is equal to beta into IB, I am not deriving this part, this you will get from device operation. Therefore, beta into IB plus 1 plus beta into IC naught. I will use this equation more often when I start DC analysis to speak about Q point stability. Therefore, that equation is very important. Therefore, if you observe clearly, what is this? This is nothing but your base current. The current what you are entering or what you are trying to enter into base is IB, and then whatever you are getting at the output, let us say this is IC. Then what is the relation between IC to IB? Remember, this equation is true only when the transistor is in active region. This equation is not valid in saturation, and that equation is not valid when the transistor is in cutoff. This equation is valid only when the transistor is in active region. Okay? Then, therefore, what is the relation between IC to IB? IC is equal to beta into IB plus 1 plus beta into IC naught. I think you know what is IB, which is nothing but your base current, and what is beta? Beta is nothing but current gain of your transistor with respect to IC and then IB. I think I can say alpha. Alpha is current gain between emitter current to collector current. That is close to 1. That's why people say IC is approximately equal to IE, because alpha is close to 1. But beta, IB to IC relation, typically it will be in the order of 50. Therefore, if it is in the order of 50, whatever current you are trying to pump at the base current, 50 times of base current you will get at the collector current, right? Then what about IC naught? That is nothing but reverse saturation current of your collector junction, because when I say transistor is in active region, your collector junction is in reverse bias, there is not only the current whatever you are getting through collector due to IB, due to forward bias voltage, but there is another current called reverse saturation current that is also coming into the IC total IC equation, which is basically IC naught. Maybe you can say you can neglect for the time being the reverse saturation current. If you neglect the reverse saturation current, then your IC is approximately equal to beta into IB. Means your output current is only controlled by base current. If base current is constant, your collector current is constant irrespective of the VCE. That is what is current source, because irrespective of voltage across any element, if current is constant, then definitely means even the voltage is changing but current is not changing. What does it mean? That is nothing but a current source. But it is not ideal current source, it is current controlled current source in the case of BJT. Why? That current is controlled by, the output current is controlled by your input current. That is what is needed for amplification, right? Therefore, that part I will explain later on, but this is what is the equation which is what is supported by the transistor when that is what is in active region. Then if this is what is the case, therefore this is what, this is nothing but IC is function of IB. I am just taking this part here, but remember it is function of IB, function of beta, function of IC naught, but I am assuming the transistor is fixed, therefore beta is fixed. Temperature is fixed, therefore IC naught is fixed, because your IC naught is depending on temperature, reverse saturation current, because reverse saturation current is depending on minority carriers. Minority carriers are depending on temperature, bond breaking, electron hole pair production. Okay, if temperature is constant, IC naught is constant, and if transistor is fixed and the temperature is constant, beta is fixed, only it is depending on IB, that is what is your input base current. Therefore, that is the reason why this is nothing but current controlled current source. This is nothing but current controlled current source. But remember, this is what is ideal model. This is what is ideal model. Therefore, when I say ideal model, I can say whatever we had seen in the case of diode, right, when it is in forward bias or reverse bias, ideal model, right, level 1 or approximation 1. Similarly, level 1 or approximation 1, that is what is when the transistor is in active region. Remember, for every region we have ideal model, practical model, ideal model, practical model, similar ideal model and the practical model. What is practical model of current source? Practical current source, right? When you say ideal current source, then ideal current source means even though what voltage VCE is changing, your current won't change. But practically, there is something called base width modulation. Due to base width modulation, if you change collector to emitter voltage, your IC will change due to VCE, not only IB. Yes, IB will control your IC, but your IC is also function of your collector to emitter voltage. That is nothing but practical current source, where the practical current source current changes with respect to voltage across the current source. Therefore, how will you represent that? This is what is ideal model. Now, therefore, this is nothing but ideal model. This is ideal model. Now, let me give you the practical model, which is practical current source. Then people represent it as current source, but with some resistance. This is nothing but practical current source. This is collector, this is emitter, but this is controlled by your IB, and this is what is your output resistance. Let us say small r0. See, because this is non-linear element, when I speak about resistance, we have to define dynamic resistance, because I already explained this. If you take current source, but it is a practical current source, the internal resistance of current source, because current source is non-linear element, then internal resistance of current source should be defined dynamic way. That's why I am taking small r0, which I already explained in the starting of the classes, which are like ideal current source, practical current source, ideal current source, ideal voltage source, ideal resistor, etc. Therefore, this is what is your practical model. This is also current controlled, but this is practical current controlled current source due to actually this R0, right? This is due to base width modulation. Due to base width modulation means your IC, maybe if you ask me, I'll tell you that also, but this is what is your practical model. This is practical model. Therefore, if you ask me the current, I don't have the space here. Therefore, if you ask me the current IC, therefore IC is equal to beta into IB plus 1 plus beta into IC naught, right? And whatever current you have, this plus there is some current which is nothing but whatever we have, I can say something which is what is depending on, let us say K into VCE, where K is nothing but what? Current, right? Then it is nothing but 1 by resistance, which is you can take in, this is DC equation in AC domain, that will give you some R naught, but what it may be qualitative I am explaining. Therefore, what is this? Your IC is not only function of IB, it is also function of VCE. Therefore, if you ask me with respect to the graph, that is what people say output characteristics, output voltage. What is output voltage? VCE. Output voltage is nothing but your VCE. Then what is your output current? That is nothing but IC. Right? Now let me take IB constant. If IB is constant, if you take ideal model, if IB is constant and the temperature is constant, then definitely your IC is also constant, right? Therefore, let me take it as, this is what is your, let us say this is what is 0.2, because it should be greater than or equal to 0.2, then this is nothing but your IB. For a given IB, therefore tell me what is your, for a given IB, your IC is constant, right? If you increase IB, your IC is also increasing, right? Therefore, if you increase IB, let us say this is IB1, this is IB2, right? For a given IB, your IC is constant, that is nothing but your IC1. And then if IB is different, you'll get IC2. This is what is ideal model. This is what is ideal model. That is what people represent from output characteristics. Therefore, if you give IB3, you'll get IC3. That is what is ideal model, where it is absolutely constant current source. If it is constant current source, yes, it is expecting, right? That is what I already explained. Irrespective of voltage, my IC should be constant. Yes, this is constant, but the value is controlled by IB. That's why this is what is current control current source. But if I incorporate the practical model due to base width modulation, right? What does it mean? The IC is not only a function of IB, right? Let us say for a given IB, your IC is fixed, but now it is depending on VCE also, which is nothing but practical current source. Therefore, if VCE is increasing, your IC also will increase. Therefore, if VCE is increasing, your IC will increase. Therefore, for a given IB, if VCE is increasing, right, then your current also will increase. This is what is your practical model. Therefore, these are all due to base width modulation. Due to base width modulation. That is what is your ideal current source. This is what normally people represent from output characteristics. Okay. Write down the third one. This is nothing but your active region summary. Okay. Take it. I think this summary is enough to understand the DC analysis and then AC analysis. That's why I'm saying all these things are coming under fundamentals, because we didn't start even the BJT amplifier, but we need all these things before starting the amplifiers portion. It is like prerequisite topics to cover amplifiers portion. Therefore, I am just giving you level 1, level 2, or approximation 1, approximation 2, like PN junction diode, approximation 1, approximation 2, but approximation 3 is also given in the case of PN junction diode, but here I am stopping with approximation 1, approximation 2. But if you continue, we have so many levels, incorporating the frequency response effect like capacitors, etc., then the model, the equivalent circuit of your BJT will be complex, which we don't need right now. Therefore, level 2 is more than enough for us to solve. Therefore, remember, this is true only when the transistor is in active region. If transistor is not in active region, this is not true. And we want current source, ideally ideal current source, to get better amplification. Why we need current source to get amplification? That part I'll explain in the coming sessions. The K is constant. Simply you can take it as constant. I want to say that your IC is function of VC, therefore I kept K. But that K can be replaced by your R naught, 1 by R naught. Over? Okay. Now, with this I can say BJT fundamentals are over. Similarly, I'll try to give for MOSFET also. Therefore, you can compare. Okay. See, in the case of BJT, this is current controlled current source. In the case of MOSFET, voltage controlled current source. Your input voltage will control your output voltage, output current. Okay. That is also current source, but voltage, input voltage will control output current. Okay. But whatever we had seen now, maybe to be short, just don't write, listen. To be short, very simple. When VBE what I can do, okay, when VBE is less than 0.7, right, then immediately the transistor is in, therefore immediately transistor is in cutoff with respect to circuit. And number 2, quick summary, when VBE is greater than or equal to 0.7, then it depends on 2 things. When VCE is less than 0.2, less than or equal to 0.2, then transistor is in saturation. If VCE is greater than 0.2, then transistor is in active region. Okay, this is what is the very quick summary to understand. Okay, you can write down. Therefore, with respect to VCE, that is what people say. Maybe with respect to graph, again the same thing. With respect to graph, if you ask me, right, therefore this is what your VCE and this is what your IC, right. Now let us say this is what it is for a given IB, right, and this is what is your 0.2, right. Now if I extend VCE curve, then actually the current will be going like this. Therefore, now this is what is the portion, right, this is what is your saturation. That's why people speak about this as saturation, and people speak this as active region, and there is something called IB is 0, approximately IB is 0, then IC will have IC naught. This is what is your IC naught, right. Then when IB is 0, then this is what is called, this is what is cutoff state. That is what you study from. I'm just taking one IB. If you take IB1, IB2, IB3, that is completely what? Because VC is greater than 0.2 and VB is greater than 0.7, that you will get completely active region. But when VC is less than or equal to 0.2, that is what your saturation region. Then when IB is equal to 0, right, then your IC is approximately equal to, or your IC is not above saturation current, then that is what your cutoff state. Therefore, in this cutoff state, this is absolutely open. In the saturation region, it is almost short circuit. In the active region, that is a current source. Okay. That is what. This is what is very quick summary based on the points what we discussed till now. Okay. If this is over, I can explain for MOSFET that I can say the fundamentals portion, right, or chapter 1 is over. Over, done. Write down MOSFET. I'm not explaining device operation, I'm just giving you the summary, okay? Similar to BJT, but in the case of MOSFET, there is no input current like your base current, okay? Now, okay, now directly I can give you the summary part, okay? If you take your MOSFET like your BJT, let me take BJT with the help of BJT, or let me try to correlate with respect to BJT, right? This is base. Now write down heading is MOSFET. All these things under MOSFET. Therefore, this is what. Now, if you ask me what is this under MOSFET, if you take the symbol of MOSFET, there are many symbols, but let me take the analog symbol. This is what is drain, this is source, and this is gate. There is something called bulk, but bulk is always connected to ground for NMOS, and bulk is always connected to VDD or highest power supply in the case of PMOS. Now that is not shown because the bulbs are connected to the fixed voltages, therefore no need to show. These are all variable voltages, therefore we need to show. Therefore this is what. See, when I say collector, this is what is drain. As I told you, collecting the carriers, draining of the carriers. Emitter, emitting the carriers, but the direction of the current is opposite. Means electrons are flowing like this, means emitting the carriers, then opposite to electron flow is nothing but your current flow. Therefore, this is what is current flow, but I am speaking with respect to carriers flow, okay, or electrons flow. Therefore, emitter is the one which is what is emitting the carriers, source is the one which is what is sourcing the carriers, okay. When I speak about VBE, here this is VGS. When I speak about VCE, here this is VDS. When I speak about common emitter, that is common source. When I speak about common collector, that is common drain. When I speak about common base, that is common gate. Okay? Those things we see later on, but now this is what is the configuration. Now, we know that, maybe I can say with respect to MOSFET, right? Now the first one, the gate to source voltage. How we have in the case of BJT the VBE, right? If that is what is greater than or equal to 0.7, then only it starts conducting. But if VBE is less than 0.7, this is not conducting. Similarly, there is something called threshold voltage. There is something called threshold voltage because I am explaining for enhancement type MOSFET. That is what is typical transistor. When I speak about MOSFET, that is typically enhancement type MOSFET, not depletion type MOSFET. We have depletion type MOSFET also. What does it mean? The channel will be present from the fabrication point of view from time t is equal to 0 without applying any gate to source voltage. But this is enhancement type, which we need to form the channel, right, before applying drain to source voltage to get the current through channel. But this is enhancement type, therefore we need to apply some gate to source voltage, which is nothing but threshold voltage. Okay, therefore if VGS is less than threshold voltage, if VGS is less than threshold voltage, then there is no channel between drain and source. If there is no channel between drain and source, your ID will be 0. Therefore, if you ask me, this is what is called, therefore this also people call it as transistor Q, right? Therefore, people call this as what? This is what is cutoff. Similar to your BJT, right? But in the case of BJT, VBE less than 0.7. But here VGS less than VT. But here VT is not fixed. It depends on process. But in the case of BJT, that is fixed, almost fixed. For a typical doping, that is 0.7. Okay, that's fine. When VGS is less than VT, your transistor is said to be cut off. Then what is the equivalent circuit? This is drain, source, gate. Then this is what is your open circuit. This is what is again ideal model. But if you take practical model, because maybe little bit I can explain. If you take the cross-sectional view of your MOSFET, this is N plus, let us say this is what is your SiO2 and this is what your gate, right? This is gate. Now this is what your substrate, P substrate, then this is bulk, okay, and this is what is your source and this is what is your drain. Okay. Now, what is this? This is basically P-type semiconductor. When I say P-type semiconductor, can I write it like N and then P? When I say N and P, you can write like this: N-type and then P-type. No, P and then N-type. Therefore, if you see between drain and source, we have back-to-back PN junction layers. Back-to-back PN junction layers. If that is what is the scenario, then if you don't apply any gate to source voltage, right? That is when VGS is equal to 0 or VGS is less than VT, right? Then there is no channel. If there is no channel, then the current ID is equal to almost 0. Even though this is conducting, because this is not conducting, in series always current is dictated by highest resistance path. Your reverse bias PN junction is having almost infinity resistance, right? Under reverse bias, then your current is almost 0. But still there is a current which is due to minority carriers, and that is what is called reverse saturation current. Therefore, it is not 0 absolutely. If it is 0, then ideal case, practically it will be in the order of mega ohm. This is what is your practical model. Therefore, if you ask me, therefore what is your ID? Your ID is almost 0 for all VDS. For any value of VDS, right? Provided if VGS is less than VT, then your ID is almost 0 for all VDS. Okay, that is what is case 1. Now case 2, VGS greater than or equal to VT means now you are applying gate to source voltage greater than or equal to VT, something like VBE greater than or equal to 0.7. Therefore, VGS greater than or equal to VT. When VGS is greater than or equal to VT, then indirectly source is connected to bulk. Therefore, you will get channel formation. Once the channel is formed, when you apply drain to source voltage, you will see the loop current. That is what your channel current between drain and source. But the channel formation is depending on gate to source voltage. And that the gate to source voltage is the one which is what is controlling your output drain channel current. Okay. Now, and there is something which I am not deriving, but you take it as granted. Like in the case of BJT, which I derived a little bit, VCE greater than 0.2 or less than or equal to 0.2. Similarly, we have some condition with respect to VDS also, and VDS if that VDS is less than VGS minus VT, and if VDS is less than VDS minus VT, VGS minus VT, then this is what is called your transistor is said to be in linear region. Basically, I can say VDS is smaller. Very simple. What it may be, VDS is smaller. When I say VDS is smaller, for small voltage of VDS, it is simply a resistor. After forming the channel, it is between drain to source, it is nothing but N-type semiconductor. If it is N-type semiconductor, it is nothing but a resistor, right? Therefore, that is what is called linear region. Why it is called linear region? In the case of transistor BJT, this is what is called saturation region, which is on. Your BJT will be acting as a short circuit in ideal model, but here it is also almost short circuit. Therefore, if you ask me the MOSFET in this is a drain, source, then gate, right? This is ideally short circuit. This is what is ideal model, but practically it will have some on resistance. It will have some on resistance. Drain and source, or people call it as R, people call this as RD, the drain resistance under linear region. That is what people call, okay. What it may be, this will be in the order of, see in the case of BJT, tens of ohm, but remember this will be in the order of hundreds of ohm. It is not 0. In the case of BJT, you can take it as 0. On resistance of forward bias. Yesterday we solved a problem, right? The forward resistance of a PN junction diode at current is equal to 10 milliampere, right? We got around 5 ohm. Therefore, the PN junction diode on resistance will be in the order of 5 ohm, 10 ohm. But if you take MOSFET, because it is simply N-type semiconductor bar, it is associated with the length of the material and width of the channel and then thickness of the channel. Therefore, the resistance it is not in the order of tens of ohm. The resistance will be in the order of hundreds. Okay. This is what is practical model. This is what is practical model if BJT is in linear region. Why it is called linear region? Because it is a resistor. If it is a resistor, right, then when you apply voltage VDS, the current will increase linearly. That's why linear region. Or following Ohm's law, therefore people call this as ohmic region, or people call this as triode region. The name triode has come from vacuum tube operation, right? Or this is also called active region. Don't confuse. In the case of BJT, this is not active region. In the case of BJT, this is saturation. But in MOSFET, active region, saturation, both are vice versa. Okay, this is what is active region. Okay, done. Now, if you ask me what is the ID with respect to VDS, now this is what your ID linear. Okay, this is what is ID linear, the linear ID current. Okay, now if you ask me what is linear, actually there is a derivation of ID which I am not deriving now. But if you take ID, the derivation ID is equal to mu n Cox W by L into VGS minus VT into VDS minus VDS square by 2. This is what is our ID current equation, assuming that there is a channel formation, right, when VGS is greater than or equal to VT. Remember, this equation is true only when VGS is greater than or equal to VT. Okay, then after channel formation, then when you apply VDS, how the current is changing? The current is changing with respect to VDS, something like this, for a given VGS. Then we know that the region, linear region, is nothing but what? VDS is very small value, which is very much smaller than VGS minus VT. If VDS is very much smaller than VGS minus VT, I can neglect the second order because VDS is very small, then VDS square, you can neglect it. Therefore, you can say ID linear, the linear drain current, neglecting the second order because VDS is less than VGS minus VT, or I can say VDS is close to 0, then VDS square will be almost 0. Then mu n Cox W by L into VGS minus VT into VDS. This is what it is, right? Therefore, if you calculate what is that R on R, therefore this is what is ID linear with respect to VDS. Okay, then if you ask me R on or RD linear, then if you calculate, you will get what? What is the definition? Delta VDS divided by delta ID, because this is what is linear resistor, right? Whether it is static or dynamic, both are same because this is linear. In this case, when MOSFET, completely MOSFET is not linear. MOSFET when that is in linear region, therefore MOSFET under linear region. Therefore, this is a linear resistor. If this is a linear resistor, you can take either static definition or dynamic definition. If you take both, that is fine. Therefore, if you take it, which is nothing but VDS divided by ID, VDS divided by ID, if you do, you will get 1 divided by mu n Cox into W by L, don't separate L by W, W by L is nothing but strength of the MOSFET into VGS minus VT. This is what is your RD linear. Therefore, the on resistance of your MOSFET is depending on what? I'll explain one by one later on after completing the summary part. Therefore, mu n, Cox, W by L, VGS minus VT, VDS, etc. Right? I think VGS is known to you, that is what your gate to source voltage, and VDS is also known to you, that is nothing but drain to source voltage. VT is known to you, that is nothing but the minimum gate to source voltage required to form the channel. That is what is called threshold voltage. When VGS is less than threshold voltage, then there is no channel, it is cut off state. When VGS is greater than or equal to VT, there is a channel formation. That is what I already explained. Therefore, VT is nothing but threshold voltage, then W is nothing but width of the channel, and L is nothing but length of the channel. Cox is nothing but the input capacitance per unit area. I'll explain what is that. Mu n is nothing but mobility of the carriers which are there in the channel. N-type carriers, because you will get N-type channel between drain and source. Okay, but anyway, I'll explain one by one after completing this. And your resistance, right, is what? Mu n is constant. If temperature is constant, mu n is constant. If device geometry is constant after fabrication, right, Cox is constant. After fabrication, W is constant, L is constant. Therefore, after fabrication and temperature is constant, VT is constant. Then only variable is nothing but VGS. That is nothing but your gate to source voltage. Therefore, if you change gate to source voltage, your RD or the resistance on resistance will change. Your on resistance will change. Okay, but that is not the case in the case of BJT. In the case of BJT, the on resistance is, it is almost 0, or I can say 5 ohm or 10 ohm, but here it is significant, and that it is what is controlled by your gate to source voltage. Therefore, let me call this as, this resistance is controlled by gate to source voltage. That's why people call this as voltage controlled resistor. Voltage controlled resistor or variable resistor. This is called as voltage controlled resistor or variable resistor. That is what is practical model. But if you consider ideal model, that is short circuit, nothing. But always not ideal model. If you go to practical scenario or practical circuit solving, then we have to consider this. Then that is what is your voltage controlled resistor or variable resistor. That is what it is. Okay, try this. Then I'll give you the third one and the last one, which is nothing but saturation region of MOSFET. Then after completing this, maybe in the next session, I'll try to correlate BJT to, or I'll try to compare BJT to MOSFET just to get some idea, therefore no confusion further. Because swapping of active region to saturation region, then it may confuse you, but I'll try to correlate both of them in the next session. Okay, take it. Maybe I can say if VGS is increasing beyond VT, then your resistance will decrease basically. If you have more gate to source voltage, more channel formation, more conductivity, then lesser resistance of the channel. That is what it is explaining. And this is what is called conductivity modulation. The conductivity of the channel is controlled by the gate to source voltage. Ultimately, the conductivity of the channel is controlling the resistance of the channel between drain and source. Okay. Now the last one, third one, VGS, there should be channel formation, no doubt about it. Therefore VGS should be greater than or equal to VT, and if you apply more VDS, or I can say from the starting of VGS minus VT is greater than or equal to VGS minus VT, then this is what is called Q. The transistor is said to be in saturation region. The transistor is said to be in saturation region because when you apply large VDS, maybe after forming the channel because of VGS, after forming the channel, right, then when you apply VDS from 0, you will see linear current. That's why linear region. But as you increase your VDS, expecting the current to be increasing linearly, but you know, because of something called pinch off condition which you see exactly at the drainage, then you see the current which will be saturated. That's why the name has come saturation with respect to the current, because that is what is saturated. But in the case of BJT, the name has come because the VCE is saturated. Because your IC is saturated because of VCE, because that is the reason we always say VCE sat. But here, this is what is with respect to the current, which is what is saturated. Fine. Those things you'll see from characteristics. Now, when transistor is in saturation, then what is the representation? Then when I say this is what your MOSFET, drain, source, gate. See, the voltages are defining the state of the transistor, right? Therefore, when you change the voltage, the state of the transistor is different. Same transistor having 3 terminals, right? The state between drain and source is controlled by your gate to source voltage. See, gate to source voltage less than VT, open circuit between drain and source. The gate to source voltage greater than or equal to VT, it is short circuit between drain and source. And then gate to source voltage greater than or equal to VT, but you are trying to give some VDS, then it is not now short circuit, it is not open circuit, it is something else, that is nothing but current source. Similar to your BJT, right? This is drain, this is source, but remember this current is controlled by gate to source voltage. In the case of BJT, that current is controlled by, that was controlled by base current. Okay. Now this is what is ideal model. This is what is ideal model. But if you consider practical model, you'll have some resistance. People call it as RD sat or RD. Then this is what is drain and then source. And still this is what is controlled by VGS. Therefore, this is what is our practical model. When I say this is what is practical model, and basically how we have that small output small R0 in the case of BJT due to base width modulation. Similarly, this RD is due to channel length modulation. This is due to channel length modulation. That channel length modulation part and all you will see from MOSFET action or MOSFET operation, from device physics or device operation. Now, if you ask me what is this ID? Okay, now if you take this ID, ideal model, I'm just giving the equation for ideal model. Therefore, we know that the same thing, we know that I don't have space here. Okay, we know that ID is equal to mu n Cox W by L into VGS minus VT into VDS minus VDS square by 2. This is what is our equation, right? This is what is our equation. Now we know that when VDS is equal to or greater than or equal to, when VDS is equal to VGS minus VT, whatever current you get from this equation, that is nothing but your saturation current. Substitute, therefore, what is ID sat? Your ID is equal to ID sat. Your ID is nothing but ID sat when VDS is becoming VGS minus VT. When VDS is equal to VGS minus VT are greater than or equal to, but I am taking the starting point which is VGS minus VT, then whatever ID you have in this equation, that is nothing but saturation current, right? Therefore, remember we should not use this equation. Why? This is derived from the original equation and we neglected the second order of your VDS and then we got linear current equation. Therefore, this is our original equation, that is what I am using and trying to get ID sat when VDS is equal to VGS minus VT. Okay? When you substitute that, you will get what? I don't have space. What I do, let me erase this. Then I'll stop, then we'll see the remaining things next session. Therefore, what is your ID? Therefore, your ID after substitution, your ID sat is equal to mu n Cox W by L into VGS minus VT into VGS minus VT. You will get VGS minus VT whole square and VGS minus VT, VDS square by 2, right? VGS square by 2. When you take VGS minus VT whole square common, then you will get mu n Cox W by L into VGS minus VT whole square. If you take common, 1 minus 1 by 2, which is 1 by 2. Therefore, mu n Cox W by L into VGS minus VT W by 2L, the 2 I am taking here, into whole square. This is what is our ID saturation, the saturation current equation. This is what is the saturation current equation. This is what is our ideal model, right? Now, if you take including channel length modulation, therefore, in this case, this is simply what? Your ID, right? ID sat, right? This is what is ID sat. You can call it as ID default, that is saturation current is function of VGS only. Therefore, current control current source. But if you include channel length modulation, which is another practical model, I don't have space, you try to write the practical under practical model. If you consider practical model, which is nothing but including channel length modulation, right? Then if you ask me what is that ID sat, that ID sat is equal to mu n Cox W by 2L into VGS minus VT whole square into, therefore on top of this current, right, we have some current variation due to VDS, that we need to incorporate. That is nothing but channel length modulation. I told you, right, this is a current source. Now, practical current source, right, that we need to take the internal resistance of your MOSFET, which is dynamic resistance, which is small rd, that is due to channel length modulation, okay. Therefore, for that practical model, people added 1 plus lambda into VDS. This is what is the model. 1 plus lambda into VDS, where lambda is your channel length modulation. If you take ideal model, that lambda is 0. See, majority of the problems, right, when you solve, people say that consider lambda is equal to 0. If you consider lambda is equal to 0, then there is no channel length modulation. If there is no channel length modulation, then you can take it this equation, okay. Therefore, here, if you ask me what is that ID sat, here ID sat is function of VGS, it is function of VGS, but at the same time VDS also. But mainly it is function of VDS than VGS. Therefore, this is what is current source, but practical current controls current source. Practical current control current source. Okay. Take this. After taking this, I'll stop here. Then we will continue in the next session. First of all, you draw this third one and then you can write those equations. It's better, it is easy to differentiate. It's better you write the equations whatever we derived, right? Here this part, then maybe the next parallel to your practical MOSFET equivalent representation. The coming session, I'll explain what is each parameter, mu n, Cox, W by L, right? Then I can try to correlate, I'll try to correlate BJT to MOSFET, then I can say the fundamentals are over. Then we can start The next chapter, BJT amplifiers. These things are enough for me. I'm just trying to bias before starting the amplifiers and all, because I need minimum few things related to the device. That is what I'm trying to explain. Okay. I'll try to give the output characteristics similar to the BJT part, then you'll understand. Okay. Am I going fast? I'm going slowly because we are dealing with few equations, right? Then theory also, I'm trying to correlate to the theory, how we use it practically and all. Okay. You can continue, right? Then maybe within 2 minutes the session will be over. Thank you.